We'll go ahead and get started. Thanks everyone for joining us today. This again is George Lesniak with Autel, and we're here to continue our discussion into ADAS calibrations. If you remember, last week or 2 weeks ago it was, we discussed whether or not ADAS calibration was right for your business. And if we didn't scare too many people away with that session, we're going to continue today with the first part of ADAS system and sensor technology. We're going to be discussing the actual ADAS systems that we'll find in the vehicle. And then as we go through the coming weeks and months, we'll get into part 2 of this session, covering the different sensors and cameras that are on the vehicle and how they work and how we'll interact with those components during a calibration. And then we'll get into more in depth into the technical aspects of ADAS calibrations, followed by best practices, a session of calibration myths and misconceptions. And then the last session in March will be a step-by-step walkthrough of the Autel ADAS calibration system. We'll do both a forward-facing camera and a radar calibration, so you can see exactly what will be involved with those processes and procedures. So with that said, we will move forward here into ADAS technologies. Now, if you recall from last session, there are a number of ADAS technologies on vehicles today. And again, they virtually surround the vehicle in a layer of protection and to help the driver pilot the vehicle to make driving more comfortable, especially on longer road trips, as well as making the vehicle safer in the event of a collision, but also helping hopefully to avoid collisions. Now, there's a number of different technologies that we're going to talk about, and we're really going to cover the most common ADAS systems that we'll be interacting with. By no means will we be able to cover every single ADAS system available today. There are some fairly unique systems available, but as an introduction, I really want to introduce you to the different systems that you'll be calibrating on a regular basis. Now, these systems, as we discussed, surround the entire vehicle, and they have different features and functions. They're driven by different types of sensors and components, but we're going to cover the sensors and components in 2 weeks in our next session. But what we really want to discuss are the systems that are found in the vehicle and how they function and why it's so important to understand how they function and how that relates to ADAS calibrations. So first and foremost, all of the systems that you see pictured here, basically each OEM, each vehicle manufacturer has their own version of pretty much every one of these systems. And each OEM has their own ways of implementing these different ADAS systems. If you recall, we discussed when it came to targets and things like that, that there is no consistency across OEMs. Well, the same can be said for ADAS functionality. And what really is important to understand before you get into ADAS calibrations is it's critical that you understand the operation of the ADAS system that you will be calibrating on the vehicle that you'll be calibrating. What I mean by that is, if we look at the diagram and we'll take adaptive cruise control. Adaptive cruise control does not function the same way across vehicle manufacturers. In fact, even within a singular vehicle manufacturer, from model to model, there may be differences in operation, differences in the quality of operation or the number of features that are available. The reason this is important is part of ADAS calibration is a post-calibration test drive. During the test drive, you will verify that the systems are operating the way the OEM intended. If each system has a different method of operation for each different OEM, it's important to become familiar with how each OEM implements their systems. So when you do test drive, you will know that the system is operating correctly. And if it's not, then we need to start troubleshooting as far as, is the issue an issue with the way you calibrated? something to do with target placement? Or is it simply you're assuming how the system should function, but this particular vehicle make and model functions differently? And as we get into the different technologies, I'll bring up some examples of how I've faced these exact situations as far as the lack of consistency across vehicle makes. So before we get into the actual technologies, when we get into ADAS systems, there's really two types of ADAS systems that you're going to face. Passive systems and active systems. Now, if you recall, we talked about calibrations and there being two types of calibration, static and dynamic. Well, this is different. This is the way the systems will operate or the way that they will alert the driver to a situation. So for instance, passive systems are warning only. A passive system will provide a warning in the form of an indicator on the instrument cluster, a light, a sound, a beep, a buzz, an alarm, could be haptic feedback, a vibration in the steering wheel, in the seat, or in some cases in the whole vehicle. But it will be a warning only, indicating that the system has detected that the vehicle is departing its normal operating parameters, and the driver needs to now focus on driving and bring the vehicle back into safe operating mode. When you look at passive systems that are warning only, many times you'll find the word warning in the system name: lane departure warning, rear collision warning, front collision warning, or something like blind spot detection or around view monitoring. These are systems that are only going to alert the driver that there is an issue that they need to either correct for or pay attention to. Then there's active systems. Active systems will also provide a warning to the driver in the same way a passive system will. An alert, an alarm, an indicator on the instrument cluster, a haptic feedback in the steering wheel or the seat. However, active systems take things a step further. They either attempt to correct the driver error, or they take preemptive measures and prevent the driver from creating a driver error. So things like automatic emergency braking will stop the vehicle short of an accident. Adaptive cruise control will change vehicle speed and also following distance. Lane keeping assist can help change the attitude of the vehicle within the lane lines, all the time alerting the driver that they need to continue to focus on the road ahead and monitoring the position of the vehicle within the lane. So these two different system types, passive and active, again, important for you to understand when you're calibrating the system you're calibrating. Is it passive or is it active? Because these corrections, let's say, especially when it comes to active corrections, they can act strangely when a vehicle is miscalibrated, when a target isn't placed properly, or there's a lighting issue, or your target's set at the right height, the wrong height, or the wrong distance. These systems can actually act quite squirrely, where they may provide an alert, but the active portion, where it's taking control of the vehicle operation, may not act as intended. So it's really important that you understand how the systems are supposed to act and react. So during that post-calibration test drive, you can rest assured that the vehicle is operating as intended. And it can become very important that before a calibration, you test drive a vehicle so you have something to compare to. Or if you get a chance to drive a brand new vehicle, car comes into your shop for something as simple as an oil change, and you get an opportunity to test drive the ADAS systems in that vehicle, so you'll understand how this particular year, make, and model of vehicle reacts to lane detection and adaptive cruise control and, forward collision warning, things like that. It's kind of like in the earlier days of diagnostics, especially with the lab scopes, when we started building a library of known good waveforms or known good scan data. Now we're going to be building this mental library of known good ADAS system operational techniques and values. So first, we're going to discuss probably one of the more common systems that you'll be calibrating, and they fall in the lines of lane keeping technology. Now, there's a variety of different lane keeping technology features, some basic, some very advanced. But again, they change depending on the year, make, and model of vehicle. And, again, there's no consistency across vehicle makes. So what we're going to do is we're going to discuss these systems in more generic terms. And really, when you look at the systems that are available today, they can be categorized into three basic generic categories: lane departure warning, lane keeping assist, and lane centering assist. Keeping in mind, these are generic terms. What's important to understand, and where this can become an issue, is the OEMs all have their own names for all of these systems. There could be upwards of 40 different names for just these three basic generic categories. Now, the reason I bring this up is when you're working on one of these vehicles and getting ready for a calibration, and you're going through your service information system to see how the system functions, to read OEM calibration procedures. You won't just be looking for lane departure warning. You'll have to search by the OEM name in order to find that information. So for instance, lane departure warning or lane keeping assist, Audi may call it Audi active lane assist, where BMW might call it lane departure warning. GM might call it lane keep assist with or without lane departure warning, where Chrysler might call it lane sense. Ford calls it lane keeping system. They all have slightly different names. You get into Subaru and it's EyeSight and the EyeSight module, which controls the EyeSight system. So understanding how the OEMs name these systems will help you find the service information in whether you're using ALLDATA or Mitchell ProDemand or MotoLogic or an OEM service information system. So as we move forward, keep in mind that what we're discussing is more genericized information to give you a general overview of these systems and their functionality. So we'll start with lane departure warning, the most basic of the three categories of lane keeping systems. So lane departure warning is a very basic system. By the name, it is a passive system. It generally monitors the lane lines and the vehicle's position within the lane lines, typically using a forward-facing camera mounted in the windshield, or in the case of a Subaru, mounted to the inner roof of the vehicle. So this system uses a camera to monitor the lane lines in front of the vehicle, and it judges the relative distance between the center line of the vehicle and the left lane marking and the right lane marking. And as the vehicle approaches one side of the lane marking or other, it will give a warning to the driver, and then it is totally up to the driver to take control of the vehicle and steer back into the lane. A lane departure warning passive system will not attempt to correct for driver error. It is only going to give an alert, an indicator on the dash, an audible tone, a vibration in the steering wheel or the seat, and then the driver needs to then again focus and steer back into the lane. So generally speaking, lane keeping systems like lane departure warning are operative only above a certain speed, like 30 miles an hour. Now, that is not a hard and fast rule. That's a generalized rule. Some systems might be 27 miles an hour, some are 32, but most are in the area of 30 miles an hour. For these lane departure warning systems to accurately detect the lane markings, the vehicle needs to be moving at such a speed as the lane markings become more solid in appearance to the camera. There are some newer vehicle systems that can actually detect lane lines down to 2 miles an hour, but those are generally found on brand new vehicles or higher end vehicles. So this more generic, more basic lane departure warning system I mentioned in the beginning utilizes a forward-facing camera. You'll see a note here, except for 2015 Nissans. Now, Nissan was quite unique in 2015 that they implemented a lane departure warning system that didn't utilize a forward-facing camera mounted to the windshield. Nissan found themselves in the unenviable position of falling behind their competitors. In 2015, almost every other vehicle manufacturer had some form of lane departure warning, and Nissan found themselves without such a system. So the Nissan Corporation tasked their engineers to come up with a lane departure warning system without adding additional hardware to the vehicle. So through the use of software only and utilizing the backup camera, they created a very rudimentary lane departure warning system. So the backup camera was turned on at all times above 30 miles an hour, and it monitored the lane markings behind the vehicle. The same way the camera mounted in a windshield would monitor the lane markings in front of the vehicle, and it determines or it attempts to measure the relative distance between the center line of the vehicle and the two lane markings. Nissan did the same thing with the backup camera. It's basically looking at the size of the two lane markings, and as one gets larger and one gets smaller, it uses that as an indication that the vehicle is heading towards one lane marking, and it provides a warning. Then the driver steers back, the warning goes off, and Nissan was able to remain competitive for that one model year. In 2016, they started using a camera mounted in the windshield and a more typical, more standard type of lane departure warning system. Now, as these systems become more advanced and we look at lane keeping assist, this particular system also uses a forward-facing camera, is also operative generally above 30 miles an hour, and like lane departure warning, is inoperative when the turn signals are on, because if the turn signal is on, we're basically telling the system that we are intending to change lanes. Lane keeping assist generally operates very much like lane departure warning. However, when the system measures or determines that the vehicle is too close to a lane line, it will not only provide a warning to the driver, it will also attempt to nudge the vehicle back into the lane. So this nudging is done primarily with electric power steering. And it doesn't steer the vehicle back, it just gives it a little jerk to the steering wheel to nudge the vehicle back, and that's part of the warning to the driver to assume control and steer the vehicle back into the lane and maintain that proper position. Well, I said most vehicles use electric power steering. There are a few vehicles that use the rear brakes to nudge the vehicle back into the lane. And I don't have a complete list of all the vehicles, but I do know that Mercedes-Benz is one of these vehicles. I know this because my wife drives a 2016 Mercedes, and she bought it because of all the different bells and whistles and all the ADAS functionality that the vehicle was equipped with. And the fact that Mercedes basically owns patents for almost all ADAS systems, and they licensed that technology to other OEMs, she felt that she wanted to go to the horse's mouth, so to speak, for ADAS capability, and she purchased that vehicle. Well, her particular vehicle has a staged lane departure warning system. It starts with lane departure warning, and then it goes to lane keeping or lane centering assist. I'm sorry, lane keeping assist. So when the vehicle provides a warning, if you stay too close to a lane line, it will then enter lane keeping assist and it will nudge the vehicle back into the lane by pulsating the rear brake on the opposite side of the vehicle. So when it pulsates that brake caliper, it will nudge the vehicle back into the lane. And at the same time, that vibration from pulsating that single brake caliper vibrates the entire vehicle. And it also acts as a haptic feedback. But one thing I want you to keep in mind, on these vehicles, let me relate it to you this way. So my wife's a little bitty thing. She's only 5 feet tall and she doesn't like driving in traffic. She especially doesn't like driving next to big trucks. So she generally drives in the right lane. And, in the Raleigh area and the Triangle area, the lanes tend to be a little on the narrow side. She'll tend to drive to the right side of the right lane. And that's fine with her. She stays away from traffic and, she gets to where she's got to go. I started noticing on her vehicle that the left rear wheel was always black with brake dust and the other 3 wheels were always clean. So after about 3,000, 3,500 miles, I took a look and sure enough, the left rear brake pads were much thinner than the right rear brake pads. So we took the vehicle back to Mercedes and the service advisor said, yeah, this is a common problem. We don't know exactly what's going on, but we'll get this taken care of. We'll put a new caliper on it. We'll change the pads and we'll get you back on the road. And they did. New caliper, new pads only on the left rear. And the vehicle seemed to be operating normally. Well, in about 3,000 miles, I noticed that the left wheel was again black with brake dust. And I looked at the pads and once again, the left rear were thinner than the right rear or any of the front pads. And it was at this time I had an opportunity to drive with my wife as the passenger while she was driving. And I noticed that while driving on Capitol Boulevard through downtown Raleigh, that she was very, very close to the right side of the lane and her lane departure warning was going off. And I told her, hey, move over a little bit. She says, no, I'm fine where I'm at. I said, well, don't you feel that vibration and hear the warning? She said, oh, the vibration, that's just the rumble strip on the side of the road. And I had to tell her there was no rumble strip on the side of the road. And then it dawned on me what was happening. She drives all the time to the far right side of the lane. The left rear caliper is pulsating continually while she drives, and she's wearing out the brake pads. So now that I learned this, I figure, okay, let's take the vehicle back to Mercedes, let them know there's a problem, and hopefully get them to change the left rear brake pads for me again. Unfortunately, this time they informed me that this is a known issue, and it's due to driver error. Now, long story short, and the reason I bring this up is, in the past, if you would have had a vehicle come in and you noticed that one wheel had brake pads thinner than the wheel on the opposite side, you might start looking at things like a frozen caliper or a frozen guide pin or something like that, and you may jump to a conclusion of selling a customer a service that they don't necessarily need, when all that customer really needed was education on proper driving techniques and how that vehicle works. So just something to keep in mind for vehicles with lane keeping assist. Now, if we take this system a step further, it takes us to lane centering assist. Lane centering assist is a very advanced lane keeping system in that, again, it still uses a forward-facing camera. Some of these systems will also use radar or LiDAR as backup systems because of the more advanced functionality that we're going to discuss in just a second. Now, lane keeping assist is an active system. However, it is reactive. Lane keeping assist waits until you get too close to a lane marking, and then it reacts and tries to bring you back into the lane. Lane centering assist is also an active system, but it is proactive. It's continually monitoring the relative distance from the center line of the vehicle to each lane marking and continually steers to keep the vehicle centered within the lane markings. So it's a very advanced system. In fact, many OEMs are utilizing this system and integrating it with other capabilities like adaptive cruise control, to where with adaptive cruise control engaged and lane centering assist, the vehicle can not only accelerate and decelerate on its own, it can also steer on its own, and it gives you a nearly level 3 autonomous like vehicle. So again, this is a fully proactive system. Many vehicle manufacturers are using this today, very advanced. However, not all vehicle manufacturers implement this system the same way. And here's something that I found just from my experience. In my job, I travel a lot. I rent a lot of different vehicles, and I'm always picking vehicles with ADAS capability because I'm generally going to a training session or to a demonstration where we have to use that rental car as a demonstrator vehicle. So I'll generally test out these systems beforehand. And what I've noticed is certain vehicles, you take, for instance, my wife's Mercedes or a Hyundai Kia, a Honda, Toyotas, those vehicles tend to implement lane centering assist very well. They maintain the center of the lane almost exactly with very little wandering back and forth. However, I've had some lower end Nissans and lower end Mazdas that basically drove like they were in a pinball game. The vehicle just bounced back and forth from the left line to the right line, just back and forth, and it wouldn't attempt to steer until it got close enough to a line that it would steer back, but then it would overcorrect. And that was normal operating condition. That's the way that system functions. So you could get into a vehicle like a higher end Hyundai Kia that tracks perfectly straight, and then maybe the next vehicle that you're going to calibrate is going to be a low-end Nissan, which doesn't implement the system as well. And if you weren't familiar with that operating characteristic, when you went to perform your post-calibration test drive, you may think that there was an issue. This is where it becomes very, very critical that you become familiar with as many different makes and models of vehicles as possible and how they implement their ADAS functionality. Now, when we look at these lane keeping systems, they're not perfect. In fact, if you go to your service information system and pull up just about any year, make, and model of vehicle that has lane departure warning or lane keeping assist, lane centering assist, and go through the calibration procedure, you'll see towards the bottom of the procedure or in the description and operation, there will be a list of when this system will not function properly. So things like vehicle related issues, if the windshield is dirty, if there's dust and road debris and mud and snow on the windshield, or the windshield wipers are worn, leaving streaks, especially in front of the camera. If the camera can't see properly, the system can't function properly. So again, ice or snow on the windshield or a damaged windshield. So if you have a crack that travels through the in front of the camera opening, that will definitely impact how well a lane keeping system can function. Glass quality is critical. So glass quality comes in a lot of different areas. So there's clarity, there's color, there's quality, there's curvature, and all of these add up to how well the camera can focus through the glass. So a perfect windshield, a brand new OEM windshield, hopefully will be as good as it's going to get. But I've seen some very low quality aftermarket windshields that actually have a ripple in the surface of the glass, that when you look through the glass, especially through the camera, the image is very distorted. I'm not saying that aftermarket windshields are all bad. In fact, most of them are very, very good, but there are a few that are not so great. So that, glass quality becomes an issue. Frit Fitment. Now, for those of you not in the glass business, the frit is that black band around the windshield. And it's especially around where the camera or the rearview mirror is mounted. So that frit or black band is going to have a cutout for the camera to see through. I've seen many low quality aftermarket windshields where that camera cutout is mispositioned. And when you mount the camera, it's partially blocked, or its view is partially obstructed by that malfitting frit. So if you're having issues with a calibration, you may want to take a close look at the windshield from the outside looking in to ensure that camera lens is not being obstructed. So objects on the dash can cause reflections into the windshield that can cause issues for a camera. I actually have run into this issue more than once with a simple piece of paper on a dash that was causing errors during a calibration. The reflection in the windshield was being picked up by the camera and the calibration would fail. So just, ensure that that dash is clear of any objects that could cause any type of a reflection. And damage or improper camera bracket. If the camera isn't sitting in exactly the OEM required position, the systems may not be able to function properly. Then there are environmental issues. So adverse weather. Most of these systems will not function properly in the rain, the fog, heavy snow, sleet, hail, things like that. When you would think safety systems should function, the systems actually will kind of shut down under adverse weather conditions. Lane marking conditions. This is probably one of the biggest issues that we face in the country, preventing us from getting fully autonomous vehicles on the road, is the lack of consistency and quality of lane markings. I've driven on roads in New York where the lane markings are not the same size from left to right. And that causes issues with lane centering assist, because they are generally looking at the lane markings and determining how close you are to a lane marking by its relative size. And if the left lane marking is twice as big as the right, I've actually had vehicles try to steer me away from the left lane marking and push me into the lane next to me because it thought that I was getting too close to a lane marking. Glare. Glare off the road, glare on the windshield can blind a camera. But there's also issues when older roads are repaired with tar. A road gets a crack, it's repaired with a tar strip, and many times that tar strip may be right down the center of a lane. If you're driving into the sun could reflect off of that tar strip and appear to the camera as a white line. And it thinks that you're outside your lane marking. I had an issue with a Nissan that tried to steer me into oncoming traffic. These things happen, so just something to keep in mind. And then, of course, there's calibration related issues. So an improper calibration. You didn't use the right target, or you weren't at the right distance, or you didn't do your measurements properly, or you didn't perform a complete calibration. And what I mean by that is there are certain vehicles like a Subaru that it's a dual calibration, static and dynamic. And if you don't complete the dynamic, the system may not function properly. So there's a lot of issues that can cause these systems to function improperly, as well as the way that they were implemented into the vehicle in the first place. So next system we'll discuss briefly is adaptive cruise control. Now, adaptive cruise control is probably the oldest ADAS system found in the United States. Mercedes had their system called Distronic. It was a radar-based adaptive cruise control back in 1999. And most vehicle manufacturers today are still using radar as the primary input for their version of adaptive cruise control. Now, again, I'm using adaptive cruise control as a generic name. Every vehicle manufacturer has a different name. So you'll have to search through service information to find out exactly what those are. But there is an ASA document that ASA, working with SAE, has put together a document of all the different names of these systems from different OEMs, and they're trying to convince the OEMs to standardize the names of these systems to help not only consumers, but also technicians in the field when it comes to servicing these systems. So the adaptive cruise control, again, primary input is forward-facing radar. Some may utilize a camera as a backup. Some vehicles like Subaru use the EyeSight stereo camera as the primary input. And other systems will be laser or LiDAR based. Toyota had a laser-based system back in the early to mid in 2010, 2012, that time frame, had laser-based systems. In fact, on some of the newest Toyota vehicles, like the Yaris base Prius, and there's another vehicle in there, a Corolla, they use a laser-based system. The laser is mounted on the windshield, though, with a camera. So adaptive cruise control is an active system. It's going to correct vehicle speed and following distance, depending on how the driver has set the system, and can work in conjunction with steering assist or lane centering assist. So for instance, some vehicles have adaptive cruise control that when you set it, it automatically enables steering assist. So it becomes more autonomous. The vehicle will steer and accelerate and decelerate for you. Some vehicles, you will not set a following distance, you'll set a following time. You'll set your following time in a half second, 1 second, 2 second following times, where most vehicles are actually set in distance, 100 feet, 200 feet, or 300 feet. Now, another forward-facing radar-based system, forward collision warning. Forward collision warning utilizes the same forward-facing radar that adaptive cruise control uses. So one radar sensor runs both adaptive cruise control and forward collision warning, two separate ADAS functions, one component. As we mentioned 2 weeks ago, ADAS engineers are writing software to take advantage of existing technology on the vehicle to create more advanced ADAS functionality on the vehicle. Forward collision warning is no different. So utilizing that already existing forward-facing radar, forward collision warning monitors the vehicle in front of us. And if we are getting too close or we're approaching that vehicle too quickly, and the vehicle determines that we might not be able to stop in time, forward collision warning will provide a passive warning, that audible tone of indicator on the dash or a vibration in the seat or the steering wheel. And then the driver is responsible for stopping or steering, away from the potential collision. So forward collision warning is really all about warning the driver to help prevent or at least help reduce the severity of those types of forward collisions. Now, again, some systems like in Subaru, they utilize their EyeSight camera. Some newer vehicles will utilize a laser or a LiDAR sensor to perform forward collision warning capabilities. Now, if we take this forward collision warning passive system and make it active, forward collision avoidance, again, still using the same componentry, but now it becomes active and it could actually act in more than one way. It can act by implementing automatic emergency braking and stopping the vehicle, or at least applying the brakes to lessen the impact or the severity of the impact of the vehicle in front of you. Some systems can also do things like pre-charge the anti-lock brakes and provide a warning to the driver. So when they apply the brakes, they have full braking pressure to, again, improve their chances of avoiding a collision. Some vehicles will actually cinch the seatbelt to pull you into the seat. Some vehicles will adjust the headrest to prevent your head from bouncing around and preventing whiplash. It really depends on the OEM and how they chose to implement this particular system. Now, there are some vehicle manufacturers that when it comes to, well, actually, I'm getting ahead of myself. Rear collision. Rear collision warning is not really just forward collision warning turned backwards for the rear of the vehicle. Rear collision warning actually works completely differently. Whereas forward collision warning was warning the driver of the vehicle when they were about to hit the car in front of them, rear collision warning warns the driver of the vehicle when they are about to be hit by the driver behind them. So rear collision warning generally uses a rear-facing radar. It can be passive or active. A passive system is going to give a warning. Let's say you're sitting still, stopped in traffic, and the driver behind you is not paying attention. Your vehicle will give you a warning that indicates rear collision imminent, and you'll do exactly what you're not supposed to do. You'll tense up and then get rear-ended by the vehicle behind you. So maybe a passive system in this case wasn't the best idea, but the active systems can actually act in a couple of different ways. Here is where a rear collision warning system that is active can do a couple of different things. And one of them is adjust the headrest to prevent whiplash. Another is, and there's a fine line here because different OEMs look at this differently. Some vehicle manufacturers will lock the brakes, put full ABS braking pressure to the brakes, so when the vehicle is impacted, it won't move, it won't roll forward into the car in front of you, thereby creating a multi-vehicle collision. It trusts that the crumple zones in the vehicle will transmit the collision impact and the transmitted energy that's transmitted into your vehicle. It'll transmit that energy around the passenger compartment and pass it forward. More vehicular damage occurs, but the driver is protected. Now, other OEMs will actually release the brakes. So when your vehicle is impacted, even with your brakes on, the brakes will be released and your vehicle will roll forward, thereby reducing the amount of energy transfer from the vehicle behind you into your vehicle. The thought is less energy will be transmitted into the passenger compartment, thereby there will be less bodily injury taking place. So next, blind spot. Blind spot is becoming a very, very common ADAS system, but also a very common ADAS calibration. Blind spot calibrations can sometimes be tricky because there's a lot of intricate measurements that need to take place. Most calibrations are going to be static in nature, but let's take a look at a couple of different types of blind spot systems and how they actually operate. So blind spot detection is all about detecting a vehicle in the lane adjacent to you in, of course, your blind spot. So when you turn on your turn signals and you're about to change lanes, blind spot detection will hopefully detect the vehicle that you cannot see and provide some form of warning to prevent you from changing lanes so you don't hit that car next to you. Well, blind spot detection could be radar-based, it could be based on ultrasonic sensors, or it could be based on cameras. Radar-based is most common. So blind spot detection can be passive or active. So first we'll talk about radar-based blind spot detection. So a passive system will use radars in the back of the vehicle, generally in the back corners, facing out on angles, pointing back and away from the vehicle to detect when a vehicle is in the lane, as you can see in the image. And if you turn on your turn signal, you'll get a warning, an audible tone or a haptic feedback that you should not be changing lanes. Most of these systems will also provide a visual indicator in the side view mirror, even if you're not changing lanes. So at least you'll see that there's a vehicle approaching on either side of your vehicle. And again, based on proximity of that vehicle in the detection range of the side or rear facing radar. So an active blind spot detection system, also called lane change assist, will not only provide a warning when you're going to change lanes, if it detects a vehicle in the lane next to you, it will attempt to prevent you from changing lanes. So if you turn on your turn signal, you'll get the warning. If you go to change lanes anyway, it's going to fight you. Now, you could very easily overcome the pressure that is being applied to the electronic power steering, but it's just there to give you that additional level of safety and support to prevent you from getting into a collision. Now, some systems like Honda with their lane watch use a camera in the side view mirror. Now, Honda uses it only on the passenger side. There are other vehicle makes that use cameras on both sides, and they're physically detecting a vehicle on the side of our vehicle. And when it sees that there's an object in the lane next to us, it will give us that warning that we shouldn't be changing lanes. Some vehicle manufacturers will have a dedicated blind spot detection camera. Others will use the 360 view or around view camera that's mounted in the side view mirrors to perform this particular task. Now, there's a newer feature called cross traffic warning or cross traffic alert. Cross traffic warning started as a rear facing technology that was intended to help a driver safely back out of a parking spot or back out of a garage. You've all probably experienced going to the Walmart or Home Depot parking lot, and you come out to your vehicle and you're surrounded by two massive lifted pickup trucks or SUVs, and you can't see the lane behind you. So you back out and hope that someone's going to beep at you and not actually cause a collision. Well, cross traffic is going to use either ultrasonic or radar, or in some cases cameras, to detect that cross traffic to give you an alert. That's generally a passive system. It can become active when it employs rear automatic braking, RAB. So cross traffic alert with automatic braking is another version of rear automatic braking, that when it detects that a vehicle is approaching, it will apply the brakes to stop you from backing up into that vehicle. You'll also see that there's front cross traffic warning on a lot of vehicles, radar based. In some cases, ultrasonic, although I haven't experienced an ultrasonic system yet, but radar based cross traffic alert is really used for you're sitting at an intersection and you start to roll and a pedestrian is walking in front of you, a bicycle driving in front of you. Some high-end vehicles have medium range radar for front cross traffic alert that can actually detect vehicles coming from a perpendicular lane, like at an intersection, that can give you a warning or prevent your vehicle from getting hit by someone who may be running a red light. The next technology we'll take a look at is around view. Could also be called surround view, 360 view, or bird's eye view. Around view monitoring can be a very interesting and sometimes challenging calibration, strictly because of the size of the calibration patterns on some of these vehicles. But around view monitoring generally stitches together 4 views from 4 separate cameras. You have a camera in the grille, a camera in the back of the vehicle. It could be a dedicated around view camera, or it could just be utilizing the backup camera. And then cameras generally on both side view mirrors. The reason I say generally is some Jeep vehicles that have removable doors do not use 4 cameras. They have wide angle cameras in the front and the back that will give you a stitched together 360 view with just 2 cameras. But most of these systems are utilizing multiple, up to 4 cameras to give you this overhead bird's eye view. And it's really interesting that they do this software interpolation with taking camera views that are, again, from the front of the vehicle, the back of the vehicle, and the side mirrors, cameras that are generally looking down to give you this image from above your vehicle that actually appears like you have your own personal safety drone following your car, filming you from overhead. So the stitched together image does a really good representation of showing you objects that are around your vehicle. So as you're pulling into a parking spot, backing out of a parking spot, you can see those nearby objects. Now, some systems are a little bit more advanced in that they also incorporate the ultrasonic or short-range radar sensors to give you proximity warnings. This particular system not only gives you the bird's eye view from the camera, but it also shows you on the right the proximity warning that in this case, an ultrasonic sensor picked up another vehicle, and it shows you how close you are in a red, yellow, green warning that indicates that you're getting closer and closer to this potential object that may be, pose a potential issue with your vehicle. Next is adaptive lighting. Now, adaptive headlights have been around for a long time, but adaptive headlights have gotten much more sophisticated in recent years, especially with LED lights and forward-facing cameras. So adaptive lighting, we're used to, for instance, I believe they first came out in BMW, where as you turn the steering wheels, the headlights would turn approximately 15 degrees as you turn the wheels. So the headlights would turn into a curve, or it would turn as you were approaching an intersection, you were turning around a corner. That was a great feature. But now that we have LED headlights and different types of projector beam headlights, these headlights can actually adapt to different circumstances. So LED headlights can change the shape of the light pattern depending on the type of road conditions you're encountering. So these systems will use inputs such as wheel speed sensors, yaw rate sensors, steering angle sensor, headlight level sensors, and on and on. But things like wheel speed sensors are not just about vehicle speed, it's about determining the type of curve you're driving through. As you're driving through a curve, the vehicle on the outside of the curve the wheel on the outside of the curve is going to be traveling faster than the wheel on the inside of the curve, and that provides valuable input to the adaptive lighting system. And as you can see by the images, these systems can alter the shape of your headlight pattern depending on driving conditions. So you could have your high beams on and have high beams traveling way down the road. You could actually have, as you're approaching an intersection, have the headlights widen out to illuminate oncoming traffic in both directions. But what's really getting interesting, and this goes beyond just auto dimming headlights. When the forward-facing camera or a headlight sensor detects the headlights of a vehicle that's approaching, and your high beams can turn off automatically, beam shaping is becoming much more advanced. In fact, there's a new system that's been around for a few years, and I'm not sure that it's available in the United States just yet, but it's available from Mercedes and Audi. It's called matrix headlights. So imagine that your LED headlights projected square or rectangle patterns of light, and they projected a lot of them to form the different shapes of light that you see in the image here. Well, what if a matrix headlight system that was projecting a dozen or so rectangles of light ahead of your vehicle, what if that system could turn off individual rectangles or areas in the matrix of lighting. So when a vehicle was approaching, the system can turn off only the portion of the headlight that would be blinding the oncoming driver. You could keep your high beams on, you could safely see further down the road and to the sides, but your matrix headlights would monitor the position of the vehicle and continually turn on and off segments of the LED lights to prevent the oncoming traffic from being blinded. That's the latest technology in adaptive lighting that we'll be seeing very shortly. Next technology is night vision. Now, night vision's been around for a while, but it's not super common because it's a higher cost option. It's found on a lot of higher end vehicles, but it is becoming optional on some low to moderately priced vehicles as well. Now, night vision systems work in a couple of different ways, but they're going to provide basically an infrared-based image for the driver to see that they might not have been able to see with just their normal headlights. So there's two types of night vision systems today, passive and active. This is not the same as passive and active ADAS systems. This is the technology utilized in the night vision sensing system. So passive systems are the most common, and it's because they're less expensive. They use a thermographic camera. Think of your infrared camera that you just got from your tool dealer for diagnosing air conditioning and electrical issues and cooling system issues. It allows you to see temperature changes. Well, that's basically what this does. It detects heat signatures. It has a good range up to 1,000 feet. Unfortunately, it's lower resolution. The images that you see are not crystal clear, sharp, photorealistic images. And thermographic infrared cameras are less effective in warm weather. So hot summer day, it's close to 100 degrees. Well, our camera may not be able to see a pedestrian that's walking in front of your car if everything's 100 degrees and a pedestrian is 98.6. So it does have its limitations. But it is very effective driving at night to be able to see things that you can't see with headlights alone. Now, active systems are much more high tech. It's also infrared based, but it works differently. They're less common because they're less expensive, but this uses a two-part emitter and receiver. So an active system uses an infrared camera, not just a thermal infrared sensor, but an infrared camera that will only pick up infrared light. It also uses an infrared emitter, so an infrared light that we cannot see. So imagine having your high beams on, but they're high beams that you can't see, but the infrared camera can. So the infrared emitter will illuminate everything in front of your vehicle up to 650 feet away, and the infrared camera can see it, and it will display on the instrument cluster or on the center stack or on some vehicles as a heads-up display on the windshield to show you lifelike images of what's in front of you that you can't see with your plain eyes. It's less effective in heavy rain and snow, but it is a higher tech night vision system. So here's an example of what a passive night vision system would look like. So here we have some pedestrian walking in front of a vehicle, and you could see it kind of looks like the Invisible Man with his head wrapped in bandages, wearing his sunglasses, just kind of a white blob that it's shaped like a person, so we know basically what it is. Here's another example. There's a pedestrian on the side of the road. Yes, we can tell it's a person by its outline, but the software in the system also detected it's a person. You can see there's a bounding box around it, and it identifies it in yellow to say, hey, here's something you need to pay attention to. And you can see everything else on the road. You can see trees, you can see vehicles on the side of the road, especially the vehicle on the right side of the road. You can see a heat signature from it appears to be the back of the vehicle. Here's what an active night vision system looks like. So this is more photorealistic. It looks not quite like a photo negative, but it's just a grayscale image that's very clear. You can even read the license plate on the vehicle. In fact, this is a downgraded image. If I had the original quality image, you could even read the brand of the beer the guy is drinking. They're that high resolution, or they can be. At distances, here's what a active night vision system would look like, detecting pedestrians on a path. So very clear. You can even see that they're wearing different shades of clothes. So very, very high tech. So again, today's conversation was really just an overview of the different ADAS systems that you're going to encounter as you embark on your newfound business of ADAS calibrations, and really just to make you aware of how these systems operate, and really to make you aware of the differences in how different manufacturers implement their ADAS systems and functionality. So as you move forward in your post-calibration test drives, you'll understand what to be looking for to ensure that the vehicle is operating up to OEM standards. So with that, if we have any questions.
Anybody have any final questions before we wrap up here?
Remember, you can unmute your microphone and you can ask me straight out. You could type in the chat. Well, Maddie,
All right,
you
if
must
there's
be
no
doing a really good
questions.
job, huh?
Yeah, I thought that was pretty good.
Oh, thank you. I appreciate that. Well, I hope I get to see everyone in a couple of weeks when we start talking about ADAS sensors. Well, was there a question there?
Nope.
I was just going to tell you thank you.
Oh, thank you. I appreciate you showing up, Danny.
Enjoyed it. Thanks.
I look forward to seeing you in 2 weeks.
All right, thanks everybody.
Thanks, Maddie.
Thank
Have a
you.
great
Thanks,
night.
George.